So remember what we were talking about last class? We talked about the algebra of matrices. We saw that we could take two matrices, or we take a matrix and take a scalar multiple of the matrix. So given matrices A and B, we could take, C as a number. We could take C times A. You could take the matrices A and B and add them as long as they have the same size. You could take a matrix A and flip its rows with its columns, A transpose. And you could take the matrix A and multiply it against the matrix B as long as A has the same number of columns that B has rows. So we could take a matrix, multiply it by a number. We could add them as long as they have the same size. You could take its transpose and you can multiply. I want to focus today on the multiplication. Another thing I want to focus on is this I, or I sub n, the n by n identity matrix. Matrix which basically does nothing to a vector when you multiply it. So if x is a vector in Rn, then I times x is just x. Just the original vector. If A is a matrix with n rows, I times A is just A. It acts like the number 1. I acts like the number 1. If x is just a number, 1 times x, is x. So I is just like the number 1, only in matrix form. And remember, the identity, so In is just the matrix with 1s down the diagonal and 0s everywhere else. So let me give you a definition. If A is an n by n matrix, we say and A with a superscript -1 is an n by, no, I don't like that, We say and B is an n by n matrix. Such that A times B is the same as B times A is the identity. So if no matter how you multiply A and B, you get the identity, we say that A and B are inverses. And we can write B equals A superscript minus 1, or A equals B superscript minus 1. So B equals, we read this A inverse. That's how you read that. B equals A inverse. So note, not all n by n matrices have inverses. For example, let me give you A equals just the zero matrix, the 2 by 2 zero matrix. Just keeping these small, 2 by 2. Then I don't care what B is. So if B is a 2 by 2 matrix, let's say B equals, well, I'm not going to even say what these are. So B11, B12, B21, B22, whatever those numbers are. If I take A times B, so 0, 0, 0, 0 times B11, B12, B21, B22. You can take your fingers out and do whatever you want all day. You're going to get the zero matrix. There is no way to get the identity matrix. You can't get ones here because this matrix is all zeros. So not all matrices, not all n by n matrices have inverses. If an n by n matrix has an inverse, we say it's invertible. Matrix A has an inverse, we say A is invertible. If there is an inverse, we say it's invertible. Not all n by n matrices are invertible. A non-square matrix never has an inverse. A non-square matrix never has an inverse. It's never invertible. So if I gave you a matrix like this, and I said, is that matrix invertible? You could just look at me and go, you know, Dr. Orderware, I think you got into some bad orange juice this morning. That's not a square matrix. It's definitely not invertible. But sometimes square matrices are invertible and sometimes they're not. And so one of the huge questions in linear algebra, which we're going to spend some time answering, sort of starting today, but really starting in earnest next week. Oh, that reminds me, before I forget to tell you, Monday's class, only this Monday, of all the classes in the semester, just this Monday, this one coming up, you know, 3 days from now, is going to be non-synchronous. Instead of meeting at 10 o'clock, I will prepare a video for you in advance, which you can watch at your leisure. And because I know watching a 50-minute recorded lecture is a miserable experience, I will keep it as short as I possibly can. So is that okay? So just Monday, and I'll try to send out an email or something reminding you, but I'm reminding you right now, there will not be a lecture Monday.
Is that going to be the same for math modeling?
It will be the same for math modeling, right? Yes, it will absolutely be the same. I will record 2, hopefully short lectures, you know, for the courses, or maybe I might even do it in parts. Like, you know, if I have a linear algebra lecture, maybe 2 10-minute lectures or something like that, kind of like I was doing at the end of last semester. But that's only for this Monday. Okay. So. Right, so a non-square matrix never has an inverse, and a square matrix sometimes has an inverse. And we'll see eventually why a non-square matrix can't possibly have an inverse, and why these sometimes do. So as I said, a major question, so one of the biggest questions in linear algebra is, which square matrices have inverses and which don't? Which square matrices have inverses? And hopefully it's clear what I mean when I say square matrix. It just means it has the same number of rows as columns. I don't mean like perfect squares or anything like that. Same number of rows as columns. So when you write it out, it looks like a square. So does the matrix 1, 0, 0, 1, the identity, have an inverse? Is there something I can multiply that by in either order? So let me just call this A. We know we can also call that I, the identity. Does that have an inverse? Let me come closer to your faces. Yes or no? You're being very non-committal. So yes, you're right. Yeah, absolutely it does. So if this is the original matrix, then A inverse is the same matrix, 1, 0, 0, 1. If I multiply, let me call this B right now. If I multiply A times B, then 1, 0, 0, 1 times 1, 0, 0, 1. You multiply these together, you end up with 1, 0, 0, 1. And B times A is also going to give you 1, 0, 0, 1. So if the identity is its own inverse, it's its own inverse. You can multiply the identity by itself in either order, not that you can even tell what the order is, because if it's the same as itself, then the order doesn't matter. But A times B and B times A are just 1, 0, 0, 1. So it's definitely invertible. Is 2002 invertible? It is if you can think of a matrix you can multiply against 2002 in either order to give you 1001. What do you think? I'll give you a hint. It is, can you think of what matrix you could multiply 2002 by to give you 1001?
Could you do half 0, 0?
Yeah, yeah, that works just great. So if you set b equal to 1/2, 0, 0, 1/2, and we multiply that in either order, so say 2 times 1/2, 0, 0, 1/2. Let's just do the multiplication. We'll take our fingers out. 2 times 1/2 is 1, 0 plus 0, 0 plus 0, 0 plus 2 times 1/2, that's 1. And in the other order, 1/2, 0, 0, 1/2, 2, 0, 0, 2. Take your fingers out again, you again get 1, 0, 0, 1. So the answer to this question is yes, it's absolutely invertible. So yes, and A inverse is 1/2, 0, 0, 1/2. What about the matrix 2, 0, 0, 5? Is this invertible? Yes, it's invertible. If it is, just tell me what the inverse is.
Can we do the same thing here with the half and maybe like a fifth?
Works.
Or does it not work like that?
No, that works just great. Yeah. So the answer is yes, and A inverse equals 1/2, 0, 0, 1/5. It's really easy to multiply diagonal matrices together. Basically, you just multiply the diagonal entries and everything else stays 0. When you multiply 2 diagonal matrices, we love diagonal matrices. It's very easy to multiply 2 of them together. And if you take this and multiply against that in that order and in the other order, you get 1, 0, 0, 1. So let me ask you a question. Which diagonal matrices are invertible? Just as the diagonals with the easiest, nicest possible matrices. Which diagonal matrices are invertible? So remember, a diagonal matrix is just a matrix which is 0 off the diagonal.
All of them.
So we've seen one which is not invertible already. We've seen 0, 0, 0, 0. And this is a diagonal matrix because there's zeros off the diagonal, but we had zeros on the diagonal too. So you want to modify your answer?
All of them without zeros
Yeah,
in the diagonal.
exactly. So all of them that have no zeros in the diagonal. So all the diagonal matrices with no zeros on the diagonal at all. If there's no zeros on the diagonal, you can just take the reciprocal of all the numbers on the diagonal, and that gives you the inverse. And if there is a zero on the diagonal, that's not going to work because you can't take 1 over 0. So we've certainly answered our important question for diagonal matrices, which are the very nicest kind of matrices there are. But for an arbitrary 2 by 2 or 3 by 3 matrix, it's a much harder question. It's not so easy to see if this matrix 1, 2, 3, 4 is invertible. Oops, no, I had this twice. So is that matrix invertible? Is there a matrix I can multiply against 1, 2, 3, 4 to get the identity? And I'm going to sort of reverse the order of the next part of the lecture. I'm going to show you how to find out if there is an inverse and what that inverse is, if it exists, before we talk about the reason why this is true. So what we're going to do is I'm going to give you an algorithm that will do two things. Determine whether a given square matrix is invertible. And secondly, find the inverse if it is. And then we'll circle back around and talk about why this works. This is what you do. It's not that hard. It's going to involve row reduction, again, like so many things that we do. So what you do is you take your original matrix, 1, 2, 3, 4 in this case. I give you in this example, 1, 2, 3, 4. You put a vertical bar down, just like we were going to do an augmented matrix. But on the right side, instead of putting a vector, you put the identity, 1, 0, 0, 1. So in this case, we have a 2 by 2. Now what we're going to try to do is row reduce the left-hand side. So row reduce, we're going to do row operations to the left-hand side. And whenever we do a row operation to a row, you do it on both sides of the vertical bar. Let's go ahead and start doing our row reduction. So this is already a 1 in the upper left-hand corner. I want a 0 below that. So I will leave the first row alone, 1, 2, vertical bar, 1, 0. And in my second row, I'm going to take row 2 and subtract off 3 times row 1. So row 2 minus 3 times row 1. I'm doing row reduction, the same kind of row reduction we did before. So 3 minus 3 times 1 is 0, as it was designed to be. 4 minus 3 times 2, that's 4 minus 6 is negative 2. 0 minus 3 times 1 is negative 3. And 1 minus 3 times 0 is 1. We can continue this process. We want to get a 1 here and now. So I'm going to multiply the second row by negative 1/2. So I'll leave the first row alone. 1, 2, vertical bar, 1, 0. I'm going to take the second row and multiply it by negative 1/2. Negative 1/2 times 0, negative 1/2 times 0 is negative, is 0. Negative 1/2 times negative 2 is 1. Negative 1/2 times negative 3 is going to be 3/2, positive 3/2. And negative 1/2 times 1 is negative 1/2. I'm almost finished. I just need a 0 above this leading 1. So let's leave the second row alone. 0, 1, vertical bar, 3/2, negative 1/2. And let's work on the first row. We're going to take row 1 and subtract off 2 times row 2. So 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. We've already gotten the left-hand side down to the identity. 1 minus 3 times, 1 minus 2 times 3/2 is going to be 1 minus 3, that's negative 2. And 0 minus 2 times 1/2 is 0 plus 2 times positive 1/2. So that's going to be 1. Assuming I didn't make any mistakes. So if that looked at all unpleasant, it was just because of the fractions. So notice I was able to get the left-hand side down to the identity. Sometimes the reduced echelon form of a square matrix is the identity, and sometimes it's not. This time it was. If the reduced echelon form of the original matrix A is the identity, what you're left with over here, once you end up with the identity over here, is A inverse. Let's go ahead and double check. Let's take this matrix and multiply it by this matrix in both directions. So we're claiming that A inverse is equal to the matrix minus 2, 1, 3/2, minus 1/2. And let's go ahead and try that. So I'm going to take A and multiply it by what I'm claiming is A inverse. So 1, 2, 3, 4, minus 2, 1, 3/2, minus 1/2. Let's do the multiplication in that order and see what we get.
So 1 times -2 is -2 plus 2 times 3/2. So -2 plus 3 is 1. 1. So 2 times -1/2 is -1. So 1 minus 1, 0. This is looking very promising. Lower left-hand corner. 3 times -2 is -6. 4 times 3/2 is also is 6. So -6 plus 6 is 0. And 3 minus 2 is 1. So in that direction, it worked. Let's try it in the other order. A inverse times A. So where'd you go? -2, 1, 3/2, -1/2. 1, 2, 3, 4. -2 times 1 is -2. -2 plus 3 is 1. -2 times +2 is -4. Plus 4 is 0. 3/2 minus 3/2 is 0. 3, wait, sorry. What did I get minus? Oh, no, we're good. Sorry. 3 minus 2 is 1. So in either order, we get the identity. So A times A inverse gave me the identity, and A inverse times A gives me the identity. In the procedure we used to find this matrix A inverse, we wrote down our original matrix. We wrote the identity down over here. We row reduced this, and we found that the reduced echelon form was the identity. And the matrix that appeared over here, that's the inverse matrix. Let's do this again in a different one. Let me ask you to compute the identity, assuming it exists. So is the matrix, let's say 1, 3, no. 1, 5, 2, 2. Invertible. If so, find the inverse. So do exactly what we just did with the previous matrix. Write this matrix down, vertical bar. Then the identity, and row reduce till you get this one down to the identity. Assuming you can.
So let me catch up. So 1, 2, 2, 5, 1, 0, 0, 1. Hopefully this row reduction business now is pretty clear to you. So we can start by making that a 0. We already have a 1 in the upper left-hand corner. So we have row 2 minus 2 times row 1. So that's 2 minus 2 times 1 is 0. 5 minus 2 times 2. So that's 5 minus 4 is 1. 0 minus 2 times 1 is minus 2. 1 minus 2 times 0 is 1. We already have a 1 in the lower left-hand corner. We just need a 0 in the upper right-hand corner, assuming we can get that. And so we will take row 1 and subtract off 2 times row 2. And we end up with, still we have 0, 1, minus 2, 1. In the bottom row, we have 1. 2 minus 2 times 1 is 0. 1 minus 2 times negative 2 is 5. And 0 minus 2 times 1 is minus 2. And so hopefully this is A inverse because what we have over here is the identity. Let's try it out. This time we had no fractions. 1, 2, 2, 5 times 5 minus 2 minus 2, 1. We multiply this out. We end up with 5 minus 4 minus 2 plus 2. Let's see, 10 minus 10 and minus 4 plus 5. So it worked in that direction. And the other direction, we end up with 5 minus 2 minus 2, 1. And 1, 2, 2, 5. And if you work it out in this direction, again, you get 1, 0, 0, 1. Did anybody have any trouble with that? Is there anything I can explain? Was that something you could do by yourself? Awesome. So how about this? Is A equal 1, 2, 2, 4 invertible? If so, find the inverse. And do it again. I just changed one thing, and not by very much.
I got a 0 vector at the bottom.
Oh, okay. I think that's exactly what you're going to find. So you probably took 1, 2, vertical bar 1, 0. You took row 2 and subtracted off 2 times row 1. So 2 minus 2 times 1 is 0. 4 minus 2 times 2 is 0. 0 minus 2 times 1 is negative 2.
And 1 minus 2 times 0 is 1. But you end up with a row of zeros at the bottom. Is the reduced echelon form of 1, 2, 2, 4 the identity?
No.
No, it's not. This is the reduced echelon form. 1, 2, 0, 0. That's already as reduced as it can get. You do not have a pivot position in every row and a pivot position in every column for this one. What that tells you, so this doesn't mean anything at all over here. What that tells you, since the reduced echelon form of this is not the identity, you do not have a pivot position in the second column, you do not have a pivot position in the second row, is that the original matrix A is not invertible. If you can make the left-hand side, if the reduced echelon form of the matrix is the identity, it's invertible. And if it's not, it's not. Sorry, is the identity. So when you're row reducing, you get down to the identity on the left side, it's invertible. If you don't, it's not invertible. In this case, there's no way to row reduce the matrix 1, 2, 2, 4 to the identity because its reduced echelon form is not the identity. We do not have a pivot position in the second row or in the second column. So it's not invertible.
It says A is the
So if the reduced echelon form of the square matrix A is the identity,
identity.
A is invertible. Otherwise, A is not invertible. If the reduced echelon form is anything else besides the identity, like that, say, it's not invertible. When I write PROP, that's short for proposition. A proposition is just like a theorem. It's a true provable statement. But when I write theorem, I'm saying this is like a super duper important result. And not that what I'm about to write isn't, but I wouldn't classify this quite at the same level as I would classify a theorem. But it's still something we can prove. If A is an invertible n by n matrix, and B is a vector in Rn, then the matrix equation A times X equals B. And you know how to solve this equation. We would just write this as a augmented matrix and row reduce A, and then what we end up with on the right-hand side of the bar is going to be our solution for X. So then the matrix equation AX equals B has a unique solution. So there's one and only one. There exists one, and there's a unique solution. And that solution is x equals A inverse times B. So let's go ahead and prove this. Let's start by showing that A inverse B is a solution. So if I take A and I replace X by A inverse B, we've already talked about the associative property. We know that I can write this as A times A inverse times the vector B. Oops, I forgot my vector symbol over the B. And A times A inverse is just the identity. And the identity times a vector, we talked about that, that's just a vector. So if this is my X, then by putting that in for, by putting A inverse B in for X, I get B. And so A inverse B is a solution. Let's show that that's the only solution. Say X is any solution to AX equals B. Let's multiply both sides of the equation on the left by A inverse. I've taken this equation, has two sides like any equation does, and I've multiplied both of them on the left by A inverse. You know, you could always multiply both sides of an equation by the same thing. So A inverse times A is the identity, times X equals A inverse B. But the identity times X is just plain old X. So X is this, and that's the only solution. We've done exactly what we set out to do. If A is an invertible matrix, then AX equals B has a solution, and it has only one solution, and that solution is X equals A inverse times B. So we're finished. We can put a square box, built-in box, at the end of our proof to indicate that the proof is over. Oh, and it's a good thing the proof is over because I see I'm out of time. Any questions? Well, have a great weekend. I can't say I'll see you on Monday. I'll see you on Wednesday, but hopefully you'll see me on Monday because I will have a video or two up for you then.